Welcome back, everybody. In this video, we're going to cover gas exchange, and in the next video, we'll talk about ventilation and perfusion. If you guys like this video, please comment, like, subscribe, and let's get started. So, when we start talking about gas exchange, okay, we have to start with thinking about how much air is actually getting into the alveoli, okay? So, just to get you guys oriented, here's going to be the alveoli, okay? And from the alveoli, we have this circulation, okay? So blood from the left ventricle over here is going to get pumped out to the systemic circulation, systemic being anywhere but the pulmonary circulation. And then, it'll go to the level of the tissues and then circulate back to the right ventricle, where the right ventricle will then pump it through the pulmonary arteries to exchange gas with the alveoli, and then the cycle repeats. Okay, so that's kind of what we're going to be looking at, and then we'll talk about how things can change in hyperpnea, hyper and hypoventilation, and all of that stuff. Okay, so how much air gets into the alveoli? Well, you guys remember that in a quiet inspiration, you had 500 mLs of your tidal volume. Okay, so that 500 mLs of tidal volume, you breathe that in. But does all of that air get in? Now, if you're saying no, then you're absolutely correct. Not all of it gets in. About 150 mLs of that gets lost, okay, into something called anatomical dead space. Anatomical dead space, okay? And only about 350 milliliters actually makes it into the alveoli, okay? So that actually makes it to the alveoli. Okay. Cool, so that's a little bit about dead space, but we gotta have some calculations for this. We actually have two. So we have a calculation called minute ventilation, and we have another one called alveolar ventilation. So when it comes to minute ventilation, and let's write this like this. So minute ventilation, you're actually going to have your tidal volume times F. Okay, what's F? What's F? F is the frequency of your breathing. Okay, or your respiration rate. You can also have it as RR, okay? But the F is more common. So let's take a regular example, okay? We'll say 500 mLs of your tidal volume, okay? And you multiply that by an average, let's say 12 breaths per minute, and you end up getting something around 6,000 milliliters per minute, okay? So 6,000 milliliters per minute. That's what you get. Okay, but now over here, we didn't take into account the dead space, the air that was actually lost. So now let's calculate the alveolar ventilation. Why is it called alveolar ventilation? It's because the amount of ventilation that's actually occurring at the alveoli, how much air is actually making it to the alveoli. So with that, very similar formula, you just have to account for dead space now. So you subtract for VD, which is dead space, okay? Or you know what, let's write it like this, VD, dead space. And then you multiply by that frequency. Now if you do this, same formula, you do 500 with that 150 that was lost, okay? And then you multiply by 12 breaths per minute. Boom, you're gonna get 4,200 mLs per minute. Do you see how this is about 30% actually less than this? Okay, stark difference between the minute ventilation and the alveolar ventilation when I actually take into account the dead space. Okay, so that's very important, and I would be comfortable playing around with this kind of equation. Okay, all right, so that's that. Now, another thing, when we start talking about gas exchange, we have to start talking about partial pressures. Now, hopefully some of you have heard of partial pressures before. It basically stems from Dalton's law, okay? So let's look at what Dalton's law tells us. Dalton's law says that the partial pressure of a given gas, okay, any given gas, is equal to the fraction of that gas in the atmosphere times the total pressure. Okay, the total pressure. how can I make this apply a little bit more to respiratory physiology? Okay, well, you can say that the partial pressure of, let's say, oxygen, okay, the partial pressure of oxygen equals to the fraction of oxygen in the atmosphere times the total pressure. What do you guys think the total pressure is when in regards to this scenario? Well, the total pressure would be the atmospheric pressure or the barometric pressure, okay? So we can actually kind of adjust this formula a little bit to our liking and say that, okay, the partial pressure of oxygen equals the fraction of oxygen in the atmosphere multiplied by the total pressure in the atmosphere. And that's going to give you the partial pressure of oxygen. Now, technically with this equation, you can have a partial pressure of the inspired oxygen or the partial pressure of the expired oxygen. But with the inspired oxygen, okay, it's very much steady, right? It's very much steady because the fraction of oxygen is very much steady as well. But with the expired oxygen, it's a little different because the amount of oxygen that you're expiring might actually change depending on your body's needs and metabolism, okay? So we're not going to calculate the PeCO2 because that's very variable, and usually on tests you'll be kind of given that. But just realize that this calculation is the same as the expired one, but this one is a more stable value, okay? So, okay, how do we figure out the fraction of oxygen? Well, this one you have to know, okay? And this one you always know, unless, again, you're not at sea level and you're in Mount Everest, which is about 250 millimeters of mercury, okay? So, if that's the scenario, let's get rid of this and come over here and start calculating our partial pressure of inspired CO2. O2. How much oxygen am I going to get when I breathe? Well, the partial pressure of oxygen, if we calculate it, we have to know the fraction, the gas fraction. It's about 0.2903, okay? Or 29.03, okay? But percent. You take this number and you multiply it by 760 millimeters of mercury. Okay, well, this is a unitless thing, so you just multiply it by that. You get 160 millimeters of mercury, approximately. Okay, approximately. So that's that. That's the partial pressure of the inspired O2. This is it. Okay, what about this partial pressure of nitrogen? Because you guys know that when I'm breathing in, right, the atmospheric pressure consists of three gases. It consists of CO2, consists of nitrogen, and it consists of oxygen, okay? These three gases right here, they make up the total pressure, okay? They make up the total pressure. Thus, if I were to calculate what their pressure is, that would be their partial pressure, all right? That's where this is coming from. And you'll notice that if I add the partial pressure of every single one of these guys together, I will get the total pressure, okay? Awesome. So what is the partial pressure of the inspired nitrogen? Well, again, you need to know the gas fraction for this. So it's about 0.7904, and then you multiply that by 760, and you get about 600 millimeters of mercury, okay? Notice that nitrogen has the highest pressure here. And then finally, 0.0003 is the gas fraction of CO2. It's about 0.03%, but then you divide that by 100 to get this gas fraction, okay? Remember, every time you want to get a fraction there, you got to divide it by 100. So if you see 29.03% oxygen in the air, that's not the gas fraction. The gas fraction would be divided by 100 to get you that. Okay, and then you multiply here, atmospheric pressure, as always, and then you get 0.23 millimeters of mercury. Awesome. So these are the values that you're kind of working with. Now, you're going to breathe in this gas, okay? And the major thing that I want you guys to focus on is this oxygen, right? Because when I'm breathing in, I really care about oxygen. I don't really care about any of these two. So this oxygen, we're going to breathe it in, guys. Okay, here we go. We're going to breathe it in. And as we breathe it in, okay, it will come down to the level of the alveoli, and its partial pressure will drop to about 100 millimeters of mercury, okay? Give or take. Some places say 105, you know, this is 100. It's just, you know, an average there. But anyways, so it drops out to about 100, and the partial pressure of the alveolar CO2 is about 40 millimeters of mercury, okay? 40 millimeters of mercury. All of the units here, by the way, are going to be in millimeters of mercury when we talk about pressures. So I'm just not going to write down the units anymore. You might be asking me why it drops. It's a little bit of a complex answer, and I'm not going to go through it, but it has to do with the alveolar dead space, not the alveolar, the anatomical dead space that exists. And also, when we start taking into account water vapor, that's actually going to lower down this pressure, okay? So again, it's a little bit complex with temperature calculation, but don't worry about that. Okay, so what now? Now we know the partial pressures here, and we know the partial pressures here. Okay, now we got to start thinking about gas exchange. Okay, but before we do that, I want you guys to take a look at this problem, and if you find an answer to this, leave it down in the comments, okay? If the partial pressure of the atmospheric oxygen is 250 millimeters of mercury, and the partial pressure of oxygen is 159 millimeters of mercury, how much oxygen is in a gas tank? Okay, a little bit of application for what we just talked about here and here. So if you find this, leave it down in the comments. Okay, let's talk about this gas exchange. All right, so if you guys think back to the first video when I talked about, mechanics of breathing, I mentioned that one of the key things you have to remember about respiratory physiology is pressure gradients and how things like to go from an area of high pressure to an area of low pressure. Things like to go down their partial pressure gradient or pressure gradient. So if that is the case, in order for me to exchange gas, okay, from this side of the blood that is deoxygenated, okay, so this side is deoxygenated, and this side is oxygenated, okay, oxygenated. If I was to exchange gas with the alveoli, okay, with this area, this region that's deoxygenated, would the partial pressure of the oxygen have to be high or low? What do you guys think? Well, I think the partial pressure of oxygen in this scenario would have to be low. Why? Because things would want to move from a high area to a low area to oxygenate this bad boy and reach it all the way here. Okay, good. So, what is this value? What is this darn value that I keep harping on about? Okay, I'll tell you guys now. Okay, so with that being said, the partial pressure in the venous side of the blood for oxygen is going to be about 40 millimeters of mercury. Okay, and we'll talk about how this came about. Meanwhile, look at what's going to happen. Oxygen will flow down from its partial pressure gradient, okay, to this deoxygenated side of the blood until it reaches equilibrium, okay, until it reaches equilibrium, and it makes this guy turn into what number, guys? What do you think? It makes this guy turn into about 100 millimeters of mercury, okay? So that's what's going to happen. The partial pressure of oxygen is 100 millimeters of mercury in the alveoli, okay, and it'll flow down. It'll continue to flow down until it equilibrates with this, deoxygenated side of the blood. And then what's going to happen? It'll turn into that 100 millimeters of mercury. A common question I always get asked is, does the partial pressure of the alveolar oxygen at that point drop down to about 40? The answer is no. And the reason for that is because you are continuously replenishing this oxygen storage by breathing in, okay? Think about it. You're taking 12 breaths per minute, right? On average. That's about 0.2 breaths per second. Okay, so this partial pressure of oxygen at 100 is continuously being replenished. So even when it is diffusing out, it still remains at around that 100 because if it's being replenished, Now, if you weren't breathing in, then eventually over time this would start going down to around that 40. Okay, and just continuously be getting depleted. But since you're not, and you are breathing, this won't drop, okay? Awesome. Now, this is what's going to happen. Something else I forgot to kind of mention is these little abbreviations. So P is for the partial pressure, okay, of oxygen, obviously. But what's this A? The big A is for alveoli, okay? The big A is for alveoli. Anytime you see a V, that's supposed to be for the venous side of the blood. And anytime you see this little a, it's supposed to be for the arterial side of the blood, okay? And of course we have another one where we have T, and T stands for tissue, okay? You might see these abbreviations change from place to place, but this is kind of what we're working with, okay? Alrighty. Okay, so with that said, let's continue and let's look at CO2. Let's look at CO2. That one's going to be interesting, right? What happens with CO2? Well, with CO2, the partial pressure I said was about 40 millimeters of mercury. Okay? Well, if it's about 40 millimeters of mercury, what do you think is going to be here? Higher or lower? If you're saying higher, you're absolutely correct because remember, the deoxygenated side of the blood is coming back from the tissue, so it's going to be high in CO2, right? And guess what? It's going to have to dump that CO2 off in the alveoli so we can kind of breathe it out. Okay, well in that case, it requires a partial pressure gradient that goes this way, which means this guy has to be higher and this guy has to be lower. Okay, but what is the value? Well, the value here is 46 millimeters of mercury. Okay, some of you might be asking me, why is there such a steep difference between the partial pressure gradient for oxygen and the partial pressure gradient for CO2? And I'll answer that question in a second, okay? But first, let's get this down. So again, the partial pressure of the venous side of the CO2 will facilitate the movement of CO2 down its concentration gradient, okay? And guess what? This will happen until this number turns into 40 millimeters of mercury, okay? Okay, all right, we're getting somewhere. We're getting somewhere. Awesome. Okay. Now we can follow this bad boy down. We can follow it all the way down. All right, let's go follow it down. It's going to go to the left ventricle, okay? This oxygenated blood now, right? After it's leaving the capillary. It's going to go to the left ventricle. They're going to pump down to the systemic capillaries. At this level, did the partial pressures of oxygen and CO2 change? No, they didn't change, right? So oxygen is still at 100 and arterial CO2 is still at 40, okay? At the level of the tissue, okay, this is a level of the tissue, okay? It could be any tissue you want, for example, muscle, okay? Now, at the level of that tissue, what do you think the partial pressure of CO2 is going to be at the tissue? And I put a greater than or less than number because it's kind of an average, okay? So what do you think it's going to be? What do you think it's going to be? Well, think about this logically. The tissue uses up oxygen, okay? You know, takes it to the mitochondria, goes through the TCA cycle, and you produce what out of that? You produce CO2 out of that. That CO2 contributes to this partial pressure of CO2. If that is the scenario, that CO2 partial pressure has got to be high here in order to move down its concentration gradient into the blood and, you know, go back to the alveolus so it can get exhaled out. So, okay, this value's got to be high here. That's why I have greater than. It's going to be greater than what, though? What do you guys think? Well, if you guys remember, the partial pressure of the venous CO2 was 46, right? Remember I said how things like to equilibrate? So from the alveoli, the oxygen goes from 100 to 40 until it makes the venous oxygen turn into the arterial 100 millimeters of mercury. Same thing's going to happen here. So this guy's going to be about 46 millimeters of mercury, and it's going to go around to this guy, this CO2, And it's going to keep going until it equilibrates and turns it into this. Okay? Isn't that pretty awesome? All right. What else? What else is happening? Okay. We had another one here, the partial pressure of oxygen at the level of the tissues. Again, this one's 100, and at the level of the alveoli, if you guys remember, it was what? 40 here and 100 here. Okay, so if we just take this same logic, it's going to be less than 40 millimeters of mercury here, because again, we're using oxygen in these tissues. Okay, that's cool. Now what? Now this guy is going to come from an area of high to low, all right, and it's going to keep going until it reaches around 40 millimeters of mercury. At that point, it'll stop and it'll circulate away again, okay? Right ventricle again, which will get pumped out to the pulmonary circulation to reoxygenate this blood and then go down. Notice when I say deoxygenated, technically it's not that true because we still have oxygen here, okay? It's just less oxygen than before. So how do you remember all these numbers? Well, really the easiest way to remember them is to just remember what's at the tissue and what's at the alveoli. Okay, so here's the alveoli and here's the tissue. If you just remember those numbers, you're going to be fine. What do you mean by that, Keon? Okay, I'll tell you. So if you remember the alveoli, you know that it's the same pressures in the arterial side of the blood. If you remember the tissue, you know that it's the same pressure at the venous side of the blood. And that should make sense to you because the arterial reflects what we picked up from the alveoli, and the venous side reflects what we picked up from the tissue, the waste that we picked up from the tissue. Okay? So that's why this works. So just remember those numbers and you'll be fine. Okay. That's that. A couple of more things to answer here. So firstly, we know that the major thing that's happening here is going to be oxygen is coming in at this level and CO2 is actually leaving the blood at this level. And you know what we call that, guys? We call that gas exchange, and we say that there is going to be diffusion of gases occurring at that level. Same thing occurs here. We're actually dropping off the oxygen instead, and we're actually picking up some CO2, okay? And again, we still have diffusion of gases occurring here, okay? So this process, by the way, this entire process that we just discussed, this entire process is called gas exchange or external respiration. External respiration, okay? Internal respiration would be the things that's happening inside of the cell when I take that oxygen and I put it through, glycolysis and TCA cycle, which goes to the electron transport chain. That's internal respiration. External is occurring outside here, okay? It's this little circuit. So that's that. Awesome. Now, to answer a question that I said you guys might have, why is there such a sparse difference between the partial pressure gradient for CO2 and oxygen? So first of all, what do I mean by this? The alveolar partial pressure of oxygen is 100, and the venous side is 40. There's a 60 millimeters of mercury difference there. With this guy, it's 40 and 46 here. So that's 6 millimeters of mercury. Why the difference? Why so large? In order to understand this, we have to talk about Henry's law. We have to talk about Henry's law first, okay, and then we'll answer that question. Henry's law states that the concentration of a gas, any given gas, equals to the partial pressure of that gas multiplied by its K constant. Do not get this K confused with a equation that we're going to talk about soon. That equation, the K that it has in there is a constant, and we'll look at that. But this K stands for the solubility coefficient. Solubility, I can't spell. Solubility coefficient. Awesome. What does that mean? This solubility coefficient is different for each gas, okay? And it can tell you something. It can tell you something very important. If the solubility coefficient is high, that means that you actually require a low diffusion pressure, okay, for that gas. All right? Okay, so one more time. Henry's law, which, by the way, is talking about gases dissolved in a liquid, is basically saying that the amount of gas that I can dissolve in a liquid, in this case, the liquid being the blood, so the amount of gas I can dissolve in the blood is going to be proportional to the partial pressure of that gas, okay? And with something called its solubility coefficient. Now, but here's the thing, if my solubility coefficient for a given gas is very high as compared to another gas, this actually requires a very low diffusion pressure, okay? That means that I can actually dissolve this gas in the blood for a lesser amount of a pressure gradient. That's what's happening with CO2. The solubility coefficient for CO2 is way higher, okay? So this guy has a higher K. That's why, actually, the correct way to put it would be here. So this guy has a higher K, which means that it is able to be soluble way more, okay? Way more than oxygen, okay? That's why it requires such a low pressure gradient, all right? In fact, it's about 20 times higher. It's about 20 times higher. The solubility of CO2 is about 20 times higher than oxygen, all right? So that's Henry's law, okay? Alrighty. And that's going to, answer why CO2 requires such a lower diffusion gradient. Awesome. Okay, what else? Just to quickly touch on so far the things we've talked about things that affect gas exchange. Okay, so we've talked about partial pressure, obviously. And in the next video, we're going to talk about this a bit more. But from the things that affect gas exchange, one of them is going to be surface area. The other one is going to be thickness of barriers, okay? Barriers that separates the air and the blood, okay? So for example, the alveoli and the blood, okay? And then lastly, we'll talk about this, but the diffusion coefficient, okay? Which is actually, we talked about this already. The diffusion coefficient is the K. Okay, so these three things, in addition to the partial pressures and all that stuff, is going to affect gas exchange. Okay, that's going to affect gas exchange. And we'll talk about these more in the next video. Okay, finally, a little on this alveolar CO2 equation. Some of you might have already seen this, some of you might not, but the partial pressure of alveolar CO2 can actually be calculated. And it can be calculated like this. You take the volume of CO2, okay, divided by the alveolar ventilation, okay. Now, and of course multiplied by K. Now this is what I was talking about. This K is not the same as the solubility coefficient up there, okay. This K is just simply a conversion factor which takes into account body temperature, and it's going to adjust multiple things. But usually you'll be given this value, and also it's somewhere around 863 millimeters of mercury at sea level and normal body temperature of 37 Celsius. Okay, so it's about 863 millimeters of mercury with those assumptions. Now here's the thing. This guy, which we saw right up here, he can be calculated. He can be calculated using this exact formula, okay? But what are these things? So VCO2 is the volume of expired CO2. Okay, if you guys make this connection, where's the expired CO2 technically coming from? It's technically coming from the cells. It's metabolic waste, right? It's from your metabolism. Because I said, remember, Your mitochondria here is going to make some CO2, right? That CO2 is going to go out into the blood, circulate all the way up, okay? And then get exchanged at the level of the alveoli, and then you breathe it out, okay? All right, so that's what this VCO2 is. It's technically metabolic waste of CO2. And the alveolar ventilation as well is just going to be indicating ventilation, okay? But this is important. This is important because if the metabolic waste of CO2 rises, the partial pressure in the alveoli rises. Does that make sense? So look at this. As this increases, the gradient for CO2 diffusion increases, which means more of it is going to circulate here, and more of it will then go out into the alveoli and increase that partial pressure. Cool. But you know what's funny? This rarely occurs. Why? Because as this increases, this also increases at the same time. It increases proportionally to decrease that rise, okay? So it's very funny how that works, all right? As the volume of metabolic CO2 increases, the alveolar ventilation increases proportionally to balance out the rise in the partial pressure of alveolar CO2, okay? Very interesting, and this is highly regulated, by the way, okay? And you guys know that the alveolar partial pressure of CO2 is pretty much the same as the arteriolar partial pressure of CO2, okay? And this arterial CO2 is very regulated. It's highly regulated, okay? And in fact, when we talk about regulation of respiration, we'll see how regulated this guy is, okay? So this guy's extremely regulated in a very tight physiological range, about 36 to 40 millimeters of mercury. That's where this guy kind of resides at, okay? Anything higher or lower than this indicates hypo or hyperventilation, which we'll talk about in a second, okay? But this guy's very, very, very tightly regulated, and if it goes up, then your body will adjust accordingly with changing your ventilation, okay? Awesome. So that's that with regards to this equation. Now, finally, we got to discuss the situations as it comes to hyperpnea and hypo or hyperventilation. Okay, so how would this above diagram change if you were to go through hypo or hyperventilation? What would happen? Okay, so in a scenario of hypoventilation, what do I mean by hypoventilation? When I'm talking about hypoventilation, I mean you're not breathing enough. You're not breathing enough. So what happens? Let's take a look at this diagram. If you're not breathing in enough air, what happens? The oxygen levels of the alveoli start to go down, and the CO2 levels in the blood will start to pile up, okay? And your tissues are not going to get as much oxygen as well, okay? So the CO2 levels in the blood are starting to pile up, which means what? What is that called? What is that called when you have high CO2? Okay, well, let's write that down first. So we got high CO2 and we're going to have low O2, okay? That is going to be called hypercapnic. This capnic is for CO2. And then for the oxygen, it's hypoxic. So low oxygen is termed hypoxic. High CO2 is called hypercapnic. Okay? Awesome. What about if you were hyperventilating? So if you were hyperventilating, what would happen? You would actually breathe out a lot of CO2. You would breathe out a lot of CO2. So over time, guys, your CO2 levels in the blood would start going down, okay? And your oxygen levels might go up, okay? Might go up. So in that case, you would actually have very low CO2 because you're breathing out a lot of it. And then you would have high O2. You know what it's called when we have low CO2 in the blood? That's actually called hypocapnia. So high was hyper, low was hypo. Okay? Awesome. So that's how hypo and hyperventilation work. Okay? Hypo and hyperventilation. And again, it's just very, very important. Hypoventilation is when your alveolar ventilation, okay, is actually going to be less than your CO2 production, okay, which means the CO2 is going to start building up, Okay, hyper is when the alveolar ventilation is actually greater than your CO2 production. Okay, there is a specific term we use when both of these kind of match. Okay, there's a specific term we use when that's matched, and that's called hyperpnea. So when the alveolar ventilation is increased or high, and that's going to be the same as your CO2 production, or I should say the volume of CO2. Well, when those two are high, both of them at the same time, and they're equal, that's called hyperpnea. So what is it? It's exactly that. It's exactly this. Let's bring it over. Okay, I can't bring it over, but it's that. Okay, it's exactly that. When does it occur? During exercise. Okay, so during exercise, what ends up occurring is your respiration goes up. Okay, thus your alveolar ventilation is going up, and at the same time, because you're exercising, you're using a lot more fuel and you're producing a lot more metabolic waste products. So both of these are going up. This would be that situation that I was talking about here, where this goes up, but this goes up equally to balance out the alveolar partial pressure of CO2. That's hyperpnea. That's hyperpnea. So again, just to really hammer stuff home, let's do a little comprehension right here. What do you guys would think would happen to my, let's take this, alveolar oxygen and alveolar CO2, okay? What do you think would happen if I have high ventilation, alveolar ventilation, but no change in metabolism or CO2 production, okay? What do you think would happen? Well, in that case, my alveolar partial pressure of oxygen would go up and my CO2 would go down. Why? Because my ventilation is high, so I'm just breathing out a whole bunch, but I'm bringing in a whole lot of oxygen, okay? Let's take another one. Let's say you have high CO2, which means your metabolism's high, but you have the same alveolar ventilation, so you're not increasing it. If that is the same, and if this is the case, what's going to happen is you're going to actually have a low partial pressure of alveolar oxygen, and you're going to actually have a high CO2, okay? Why? Because your metabolism is high. Maybe this would be better if I said metabolism, but either way, this would be the scenario, okay? All right. And then I'm not going to talk about hyperpnea because, that's just going to be equal metabolism versus equal ventilation. One more thing we can actually talk about. What if we are at high altitude and the partial pressure of oxygen is low? The partial pressure of oxygen is low at altitude. What do you think happens then? Okay? If the partial pressure of oxygen is low in altitude, that's only going to affect my alveolar oxygen, not my CO2. That's not going to change. Okay, so that's going to be the same. Okay, so that's going to be that for everything in this video, okay? In the next video, like I said, we'll talk about ventilation and perfusion matching, and we'll talk a little bit about the effect of gravity on ventilation. And we'll also talk about a transit time, basically how long it takes to bring this oxygen from 40 millimeters of mercury to 100 millimeters of mercury in this capillary. How long does that take, and what does the graph look like there? Okay, so that's going to finish it for this video. If you guys like it, please like, subscribe. If you have any questions, comment down below. Let me know the answer to this down below, and I'll see you in the next video.